Perfect. Go ahead. Are we good? All right, so Ventures in Infrared Communication Part 1. I already don't know what to say. We're going to talk about, we're going to carry it. This will do a better description of what we're going to talk about. So we're going to talk about infrared, what it is, why it matters, some of the uses for it, why we care about it, and then we'll progress further into the actual data communication, which is the main use that I want to focus on. That's kind of what's most relevant to what I'm working on currently. And then that last section, IR protocols, is actually kind of a subsection of data communication. So what is infrared? It's a range of light. So I imagine most people are familiar with the light spectrum. From left to right, we have long wavelengths down to short wavelengths. And then across that middle section, we have it kind of divided into the range. We have the radio waves, microwaves, infrared, of course, visible light, ultraviolet, X-rays, and gamma rays. As you're going across your wavelength gets progressively smaller and your energy increases. We're going to specifically narrow down into the infrared section. And then also, a key thing to note, people know this as the light spectrum. It's also known as the electromagnetic spectrum, and that will become relevant. So when we're talking about light, there's kind of two main models that are discussed. The particle model and the wave model. You may have heard or recall from like physics class that when you talk about light, you kind of think of it as one of these two forms. Either you think of light as a particle or you think of light as a wave. Never really both at the same time. We will be focusing on the wave in that we want to think about the wavelength and the kind of attributes that come along with light being a wave. We're not really thinking about how when light's a particle, it bounces off of physical objects. That does matter, but that's not what we're focusing on. Also, when you look at this wavelength kind of video, you'll notice that it has kind of 3 dimensions to it. As time's going forward, you have a z-axis and a y-axis. There's a polarization to light waves, and we'll talk about that a little bit more. Second, that slide meant to be taken up. So most people are probably more familiar with a mechanical wave. That's kind of what a standard sine wave behaves like. When you have a mechanical wave, you're talking about a physical kind of transfer of energy. A mechanical wave requires a medium to pass. So a mechanical wave will travel or traverse through a solid, liquid, or gas. It does not just exist in space. So an example of that would be a sound wave. In a vacuum, there is no sound. If you've ever seen the tagline to the movie Aliens, in space, no one can hear you scream, I think is the tagline. It's because there's no physical medium to carry that sound wave. When I'm speaking, there's an actual vibration that travels through the air that comes in contact with your eardrum, vibrates the eardrum, and that's what you're hearing. There's a physical transfer of that energy. Whereas with a light wave or electromagnetic wave, it does not require a medium. It can travel through a vacuum. So if you think of the sun is a giant ball of helium emitting a bunch of light and energy that travels through space, an empty vacuum or near an empty vacuum. And that comes into contact with our atmosphere. I know, it's ridiculous. So from that entire distance of the sun to the earth, that energy is just traveling through nothing. And then it comes in contact with our atmosphere and it travels through the air. So these light waves can travel through a medium, but they don't require it. That doesn't fully explain why it's three-dimensional though. And we'll come back to that in the next slide. But first, let's talk about some properties of standard waves, mechanical waves. Probably mostly review. We have the wavelength, which is the distance between your two peaks of your waveform. So from peak to peak, how long is that distance? We also have the period, the length of time it takes for one oscillation to complete. So from the beginning of one repetition of your wave to the start of your next repetition, how much time did that take? So you have the start of one repetition here, the wave starts repeating, how long did it take for that to occur? That's your period. And then the frequency is actually just the inverse. Instead of talking about how long did it take for the oscillation, it's how much oscillation do you get per amount of. So those are just inverses of each other. And then you also have the amplitude, which is the height of your wave. Also, I realize that I'm nervous and kind of anxious, probably talking really fast. If you have any questions, please interrupt me. Or if I am talking too fast, tell me to slow down, because I am not going to be self-aware of that. I'm just going to fly through this totally blind to that.
Light waves.
We will get to that. But now that I've brought that up, are there questions so far? Now that I've gone through, 5, 6 slides without opening the floor at all. Yeah. Yeah, any solid, liquid, or gas, that's, so a good example that I want to think of, or I picture, if you've ever seen like people in a gym with like a big rope and they're like kind of like snapping the rope repeatedly and that's just their workout. Yeah, I can.
I got it. We're doing this a little change on the fly. I will manage to do a little.
Thank you.
Well, together.
Also, do I need to repeat the question? Okay. So we're talking about how there's other mediums that waves can go through. So I was talking about if you've ever seen someone with a big rope and they're kind of waving the rope, just getting an arm workout. As they're snapping, they're only moving their arm vertically, but you get a wave out of it. That wave is the transfer of energy going through the rope. They're not, I don't want to say this. Yeah. You're breaking it.
Sorry, it's not showing the camera, which. Yeah. I have to do it on the fly thing. Sorry to break it.
You're fine. This is not a career-altering presentation. We'll be okay.
No, this is a problem. This is what I. Go much better. Now I can flabberdash up here and Isn't this look very nice? Back up. Back up. Perfect. There you go. And I'll go ahead and talk.
Are we good?
Good.
I lost my train of thought. We're talking about ropes.
Mechanical waves going. Talking about the gym rat.
The gym rat?
Big guy on steroids. Swinging our ropes around. Like
I was actually talking about myself, which
Oh.
actually I fit that description as you can through the video.
Okay.
I got a chuckle.
I got a. That was okay. Light is. Shut up. Shut up. This is not a professional. Still, shut up. Okay. You answered the question. Feel like you answered the question.
Probably not. I probably did not fully answer the question.
Okay.
But as you're snapping this rope up and down, the wave that you see, the kind of waves that you see the rope forming is the transfer of energy in a wave form. And the energy is passing through a solid rope. It can be any state, any, what's it called? Solid, liquid, and gas. State of matter, yeah. That's
Plasma. Ball, plasma. Wow.
yeah. Well, any other question? Go back if I finish that slide.
There we go.
So we talked about wavelength, we talked about the period, the frequency, the amplitude. Yeah, so that's good. Standard sine wave in 2 dimensions. And then when we're talking about electromagnetic wave, we kind of gain some extra properties. We pick up a few more. Since it's 3-dimensional, I think this top image demonstrates it really well. This main black arrow kind of going diagonal is time. So you can kind of see the wave as it changes through time. This blue wave, that's the electric. And then you also get the magnetic field, which is the red portion. And in this image, they kind of, if you were able to look at it kind of headlong, they'd kind of create like an X or a cross shape. But you don't always get that shape. In this bottom image, you can see there's linear, circular, or elliptical. These are the different fields of electricity that these waves create as they're traveling. The electromagnetic portion, naming of the really important when you think of them in this manner. The waves aren't just light coming from the sun to earth. It's also kind of like an electric field. If you think of like a magnet or a battery where they're polarized, they have a positive, negative. These waves have the same kind of property to them. So when we're talking about light wave properties, we have the standard wavelength, period, frequency, but we have 2 amplitudes because we have these 2 fields. They're not always the same, but they can be the same. It's like in this kind of ideal linear wave on top, the red and the blue are the same height. They're going to have the same amplitude. But if you think of an ellipse just by definition has 2 dead marker.
Oh no.
And they don't have open trash cans. I can throw it across the.
We're going to cut this out later on. Pretending through marker.
You have 2 radii when you're talking about an ellipse. The height and the width is going to be different. So you pick up 2 amplitude values, which will be different from each other. But if you're talking about a circle, that's a bad circle, pretend it's circular. You're going to have a standard R, which is just going to be your singular amplitude. but you can use it in two different contexts.
Cause like
Why are they polarized?
yeah, why does like that?
I don't have a good answer as to why you get different types of electric fields. It just is a type of an electric field. That's the extent of my knowledge. It can come in different shapes depending on how it forms. I don't know if it has to do with the wavelength. I'm not certain. We can go back to this.
Okay.
You're doing like double duty right now. And then the other thing to note about these light waves, since they can travel through a vacuum, they travel at the speed of light in a vacuum. But when they are traversing like a solid, liquid, or gas, those mediums that we've been talking about, it doesn't actually travel at the speed of light. That kind of like inhibits how fast it can travel a little bit. Slide.
Bye.
There you are. So now we're going to talk about some uses of infrared light. Basically, why do we care about it? So we've kind of defined separate regions of the light spectrum. There was like the microwave section, the radio wave section. Why do we care about the infrared light section? So one of the uses is night vision. These are night vision camera images. On the left, you just have a security image or a security camera. And I believe that green box is just part of the security software. It just tracks. That's
All that.
Imagine.
Yes.
I believe the software is probably just smart enough, kind of like dash cams, where they only store the video when something's actually happening, like when there's a collision. This camera probably just stores the video only when there's. And then on the right, that's just like video from a documentary where they're filming. That's actually a Jaguar. You can't really tell, but that's actually a Jaguar. Yeah. And then I imagine most people have seen for thermal imaging. Basic concept is just the camera is able to detect the temperature of what it's looking at, and then we change the color of what we're looking based off of. So on the left, the cold portions of whatever that is doing is blue, and then wherever it's hot, it is closer to red or white. And on the right, there's a hummingbird. Similar concept, they just use purple instead of blue. It's just a color choice. Yeah. And then meteorology, I'm certain pretty much everyone has seen types of satellite images. This is actually an application of thermal imaging where they're able to see the temperature of kind of heat waves, cold fronts forming, and how that's kind of affecting everything else around it. And of course, they project what the weather is going to be like going forward. Also interesting is they also use this satellite imaging for climatology. So they can use these images to kind of detect changes in our ozone and our atmosphere. And that's kind of how they kind of measure global warming or climate changes and type of. Yeah, I almost didn't want to say it. We can censor that part. Yeah. Next slide. Yeah. And then infrared data communication. This is, again, what we're going to focus on going forward. I'm going to take a minute to talk about this one. So on the left, we have a single data stream for IR TV. So on the left of this image, we have a TV remote, standard TV remote. And then on the right, there is a TV. So this TV remote, when you push a button, it sends a data stream out. TV will pick up that data stream. And then based off of what that data stream is, the TV will recognize what that code is. And then it will perform an action. So an example of that, you push the volume up button on your remote. It sends a unique data stream. Each button will have a unique data stream associated to it. So you push the volume up button, sends out whatever that data stream is. TV picks that up, recognizes that data stream as, oh, that's the volume up button. And it will then perform the volume up. That can be changed to any button. On the right, the multiple parallel data stream, it's kind of interesting because it uses infrared and it is infrared data communication. It's kind of an outdated technology. It is kind of cool though. The way that worked, you'd have these LED almost lamps. They're kind of big, and you'd place them around your room. And the camera on either your phone or your laptop would be able to pick up signals from these lamps. So it was basically like an early form of Wi-Fi or Bluetooth, but it used the camera. The camera picked up the signal coming from these, and you would need a few of them around your room so it could kind of locate where your device was sitting. Kind of like how in VR, it has the cameras to kind of detect where you are spatially. These lamps needed to detect where your device was and then send a signal into the direction of where it was. And then the camera would pick up that signal. Yeah. Did not really catch on because by time that was made, Wi-Fi and Bluetooth were just better in every way. And you didn't have to install lights everywhere.
The horrific alternate timeline where we all have light LED.
Well, they're infrared, so you can't actually see them. Your eyes don't pick it up. Remember when we had that spectrum? The infrared spectrum is outside visible light. You can't see it with your eyes. Yeah.
Cable flip, right? But are the bits typically as amplitude pulse?
No, they are not.
Okay. What are they? Maybe we had a little bit.
You're getting ahead of me a little bit.
We'll get to it, right?
We will definitely get to that.
Okay.
If that does not get explained by the end of the lecture, ask it again. When we get to the IR protocol, we'll go into in-depth on that.
What?
So some other uses I thought were cool. These are the kind of the ones that I personally thought were really interesting. So the Nintendo Wii, I hope everyone is in the age range to know what the Nintendo Wii is.
Never understand.
It'd be really embarrassing.
I am not that.
So this is really cool in my opinion. You have the sensor bar, which goes near your TV, and then you have the Wii remote. And then of course, what actually ends up happening is swing the remote and then the console recognizes you're trying to swing a tennis racket or roll a ball or whatever. But the way it works, the sensor bar is actually just a bank of IR light. It just has a whole bunch of IR LEDs in it that it shoots out into the room. And then the Wiimote, the controller, if you've ever held one or looked at one, there's kind of like a black piece of plastic at the end of it. Yeah, it's like a black screen. It's probably plastic. But behind that is just an IR camera. And it can see all the light that the sensor bar is putting out. And using that camera, the remote is able to determine whether it's changing positions or angles based off of how it's picking up that light. And then it sends that information to the console. So this, yeah, you cannot cover that piece for the remote to work. But the sensor bar doesn't actually censor anything. It's just a bunch of lights that it sprays out into the room. The controller is actually what picks up the light and figures out where it's at. And then yeah.
I'm sorry to that bar is probably
it's just for power. Yeah, there's people.
Controllers do.
The controller's doing all the work, and there's people that actually modify these sensor bars to plug them into like regular outlets.
That is impressive.
You don't. There's nothing special going on between the sensor bar and the console except just powering it up. Just power. There's no communication. Right. I always thought it's called the sensor bar. You'd think it would sense the motion, but it does not. It's just a bunch of LED lights.
Honestly, why? Like the bar was completely. I never.
Yeah, it's reliable. It's kind of also a cheap way to do it, which keeps your costs down. But that's also why, like if you think back to the Kinect, it was able to like sense movement of your whole body. And it wasn't dependent on a remote because it didn't use that camera built into the remote. The camera was built into that whole Kinect device, which is why the Wii remote was like $50 and the Kinect was like a whole console on its own. It was much more complicated.
Technology. I think
Put microchips in your bloodstream.
Microchips in your bloodstream. Playing the Star Wars game that they had.
So next slide, which is super, super cool. Since the sensor bar, all it does is project IR light, and candles emit IR light, you don't actually need the sensor bar.
What is where's Tenet?
I don't know how reliable this is, but it does technically work where the candles will emit IR light and the remote can pick up that light. That's all that's really required for the console to work, or the remote to work, rather. Next slide, which is also really cool. You'll see below the TV, this guy has a Wii remote hooked up facing outwards from the TV, kind of where the sensor bar normally would be. And then he put IR lights onto his camera, and the remote is able to detect where the camera is that he's filming with. And he wrote some software where it kind of creates a primitive three-dimensional VR tunnel. The image on the TV changes based off of his positioning of the camera. And it's all using the camera built into the Wii remote. I know I'm using camera to talk about two different things. This was like 15 years ago. Also, I don't have a slide for it, but this same guy kind of did the reverse, where he had the Wii remote facing his TV, and then he put an IR light onto a marker, and he basically made like what are they called, like the smart boards? You know what I'm talking about, where you can like, it's like a touch screen whiteboard. He made one of those using a Wii remote and just an IR light bulb. He has videos on YouTube. I don't remember what his. This is really cool. So of course, this is the Mona Lisa. Yeah, super overrated. What a hack. Not even good. So instead of just taking a regular photograph, this is a scan of it using IR light. And the reason they kind of wanted to do that is by using the IR light, it's able to pierce through like what standard visible light shows. I don't know. It might. I hope not. Because this is the original.
Problem if it does.
But the reason, I don't think it does, because the reason they want to do this, there's a few. One, by being able to see the underlying layers. If you know anything about painting, when you paint, you're actually building layers of paint on top of each other. So what you see on top actually covers the layers underneath. And by using this IR light, they're able to see like the brush strokes of the underlying layers, how he actually made this. And one, you can learn how he did it. Also, it's also used for, by seeing the brush strokes, you can see if it's an original because the brush strokes will be there, as well as if it's been altered, like if someone's tried to restore it or change it in any way, the brush strokes will be broken. So you can see kind of the history of the painting just by seeing its brush. Is there a question? Heard it did. Oh, okay, cool. Welcome.
Oh boy, my favorite.
So I've talked about how I really like planes. And I apologize, this is a really low quality video. It's kind of hard to find high quality video of military technology. Yeah, big surprise, I know. So this is a homing. So one of the things, huh?
Oh, stop it. We're cutting it off. Continue. Okay.
So this video isn't the actual missile itself. So you have the missile projectile, but you need to aim it. You need to set a course for it. So this is basically a super fancy IR camera, and it uses thermal imaging to kind of look at whatever your target is. And by looking at the thermal image of what is in front of you, it kind of creates a passive trajectory of where that plane or whatever is going, kind of figures out where it will be as time passes. Then when you shoot your missile, it kind of creates a trajectory to intercept the trajectory of your target. I don't know if I explained that well. Yeah. Yeah, what's up? Yeah, it's not, were you there when Nate was showing his telescope? So he was talking about passive and active aiming. So this is just passive aiming. So it kind of predicts where your target will be. It doesn't actively update as once the missile's fired, that's the end of the tracking. There's no update like if that plane kind of turns or changes where the homing thought it would be, it's going to evade the missile. Also, since it's using thermal, that's why flares can be effective because it's just a bunch of heat and it just ruins your image. You'll also see like an older plane. I am not going to draw so I'm not even going to attempt to make a good plane.
Really? All right.
So you have your like kind of body of the plane, and then like you have your wings. It's kind of like a semi top down, semi side view because I can't draw. So you have like your plane and then like where you're sitting. On older planes, they'll kind of have like this thing sticking out with this camera on it. Like when you look at it, you think that's super not aerodynamic. Why is there just this weird thing sticking out of it? It's the homing portion. And they want it to be further away from the plane so it can get a good image. Oh yeah. Okay, astrological photography. So this pink image, I believe this is the Spider Nebula. This pinkish red image is what you see with visible light. So if you were to just take your eyeballs and look into space and see this, that's kind of what you would see. And then this green overlay is a IR, infrared image. And if you go to the next slide, this is the pillars of creation. I think these are much better images to kind of demonstrate, but that video, the overlay was kind of nice. So these are the pillars of creation. On the left is just visible light. That's possibly Hubble's most famous image. Definitely one of them. I'm certain everyone's seen that. And that's what you see with just visible light. And on the right is an infrared image of the same nebula. The big thing, when I talked before about how IR is able to pierce through the layers of the painting, IR is able to pierce through all this kind of smoky light pollution that visible light gets. All those stars on the right are blocked when you're looking through visible light spectrum. So now we're talking about infrared data communication. So, parts of communication. We have in this image, we have a remote, infrared radiations, is that how it's phrased, and a television. No. Going forward, the remote will be thought of as a transmitter. It transmits signals, it sends them out. You have your infrared radiations. I'm just going to refer that as your signal. And then your television would be the receiver. It picks up text, receives that signal that's being sent out by the remote. So you have a transmitter, the signal, and the receiver. Sorry, can you go back?
Oh.
No, I pointed at you. It's my fault. If you want to liken this to like human communication, you have your mouth transmits sound. Sound travels through the air, and then your ears are the receiver. They pick up that sound. Now we can go forward. So we have the transmitter slide. So if you've done any circuitry, you'll be familiar with standard LEDs, light emitting diodes. You can get them in white, green, blue, yellow, red. I don't know. No, don't go for it. Sorry. So the way it works is you have your anode and your cathode, just your positive and negative. And when power goes through these LEDs, it emits light. The IR transmitter is different in that instead of being in regular light spectrum, it's just in the IR spectrum, but it works the same way. It's just power going through a diode. Yeah. Sometimes you'll see them on these breakout boards is what they're called. And note that this has 3 pins instead of 2. You have data, power, and ground. GND is ground, VCC is just power, and DAT is data. It functions the same way, it's just on a breakout board. So pop quiz, what is that fancy schmancy breakout board? Any guesses? Yeah.
Yeah.
Mm-hmm. 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 Okay, let me give a hint. So these both transmit signals. This top basic LED will just transmit a signal the same way as this bottom one transmits a signal. There is something about this board that is necessary. Or I shouldn't say necessary, kind of helpful. So I should actually clarify that. The data pin is actually your anode and the ground pin is your cathode. And the VCC just amplifies your signal to make it stronger. So you have power, your signal comes in through the data, and then your ground is obviously ground. And VCC is just always positive, and it provides extra power to your LED. So like my personal device, which uses these, this ESP32 isn't actually strong enough to emit an IR signal that's detectable.
Oh.
So we haven't figured it out yet. So there's something about these. These are on the bottom. There's regular LEDs on. Why would those be necessary? These kind of white rectangles, those are regular LED. Yeah, so if you go to the next slide, you're pretty close. I'll count it. It's for your eyeballs. These IR LEDs, you can't see it. It's in the IR spectrum. These are not invisible light. So this breakout board has, you can get them in different colors, whether it's red or blue or whatever. They light up when a signal's going through, and that will light up at the same time as your IR signal. An alternative to that is if you're just using one of those regular LEDs, you can kind of put it in parallel. Like if this is your IR LED, you can just put like a red LED. Terrible. You can put it in parallel with a regular LED. So this one you'll be able to see on the right because it's just a red LED. And then the IR one is in infrared, which will actually transmit the signal that you want. Or you can just get one of those breakout boards, which will light up. So then again, you can't see IR. But if you were to look at, this is a TV remote, you can't see it with your eyes, but any video camera can. So if you look through your phone camera or whatever, you'll see this kind of violet light and it blinks as it's transmitting signal. So now let's talk about the receiver. Slide. Yeah. So this is what a receiving module looks like. Couple things to note. You have a black, okay, so you have these 3 pins and then you have this black rectangle. That's what actually, I'll go into more detail later, but that's what demodulates the signal. I'll explain what that means later. And then kind of the round portion, that's the, what's it called? Not photosynthesis, photodiode. It is photosynthesis. That's what actually detects the light, the kind of round portion. It's in my slide, I don't know.
Don't end show. It's so like
It's not a big deal.
we'll talk about later.
You went from current slide. That's what actually detects the light. And the transmitters, you'll notice, if you recall, were clear. These are all going to be black. The reason for that is to block out visible light, to prevent that interference. If we go to the next slide. Sometimes you'll see these receivers with this kind of metal piece on them. That's called a Faraday cage. The purpose of that is to prevent electrical interference. So if you recall, these light waves are actually electromagnetic waves. They have an electromagnetic field. We want to block that out. We just want to look at the light signal, the photon?
Yes.
The photons. But we also want to block out visible light, which is why they're black. It prevents that from getting in. The Faraday cage prevents the electrical field from getting in. You're only picking up that light signal. In my personal experience, this is just my own opinion, the Faraday cage is more of a nuisance than anything else. It's kind of unnecessary for what I'm using, and it just kind of makes the device a little more picky on how you're picking up a signal. I find them annoying. The cage or the whole module?
The cage itself, like the.
Yeah, it does kind of have a face. And then if you go to the next slide, you can also get these on a breakout board. You see these very commonly on a breakout board, even more so than the transmitters, because these are only picking up light. If you look at them through a camera, you're not going to see anything. They're not emitting light to be seen. They're only receiving light, and these will light up as they're picking it. I thought about putting one, but I couldn't really phrase it in a way that made. So another thing, all of the modules that we saw in the previous slide had 3 pins. We didn't see like a 2-pin version, kind of like the transmitter. The reason for that is the 2-pin versions are able to sense light, but they're not able to receive a signal. So these IR light sensors on the left, they'll give you a confirmation that they're seeing an IR signal, but they can't turn it into like a command or anything. They just say, yep, I'm seeing light. That's it. Whereas on the right, they can actually turn the signal into something functional. They kind of handle that on their own. The sensors are lazy. Yeah. So protocols. So again, talking about the transmitter, the signal, and the receiver. We may have to flip through a couple. Go to the next one. I had trouble finding an actual signal image that I liked for these. So some of these are probably going to be blurry, so I put alternatives in. Up here on the top, this logic analyzer with the 4 channels, that's kind of a signal that I picked up at home with my own logic analyzer, basically an oscilloscope. And then the one on the bottom, I don't know if that's too blurry to see, but that's what I found online. I know the one before was that rare, so we're not going to do that. Yeah, that was terrible. Yeah, so when we're talking about an IR signal, well, let's talk about language first. So the sound comes out of my mouth and it goes to your ear, but there's more structure to it than that. For it to make sense to you, there's a language associated with it. You can't just make noises and expect people to understand what you're saying. We have nouns, we have verbs, we have words, sentence structure, that kind of thing. So when we're talking about IR communication, there's a language to it. We just call it a protocol. So the whole IR protocol concept is the language of IR. And just like with human language, where there's different languages, we can speak English, Spanish, Latin, whatever, there's different protocols with IR, which will vary the rules of your signals, how they're sent and received. I'll kind of touch on the different protocols. It's not really going to be the main focus. I'm just going to focus on kind of the general structure of what they have in common, kind of how it works. Don't change slides. So this kind of orange signal, we have a big block at the front, That's called the header. That's kind of the, hey, TV, I'm about to send you a signal. Start listening. Then we kind of have an empty block. I apologize for the people listening to the recording. I'm kind of pointing to the screen. I don't know. Well, they wouldn't even be able to see that anyway. So you have this big block at the front where that's called the header. Then you have a dead space. That's just, I think it's just called the gap. I don't remember. So that just kind of lets the receiver get ready to pick up your signal. Then it sends an address. If you look at the bottom image, it has an address block. It's letting the TV know that I'm talking to you. That's the address of TV. It's kind of like if I wanted to talk to Nick, I'd say, hey, Nick, I'm getting his attention. That's the address. Nick is saying, hey, Nick. That's sending the address saying, I want to specifically talk to you. And then after sending the header, the gap, the address, you then send the command, which is just whether it's the volume up button, the volume down button, whatever specific button you're trying to transmit, that's what the command is. Then you'll notice there's a long, very long gap on the right, and then another kind of big orange block. That's the confirmation. After you send a command, you have to confirm that you meant to send that. And depending on your protocol, it can be different. In certain protocols, like on the bottom, has the command and then the command inverse. Sometimes you just send a solid, like a positive signal, and that just means repeat. I should actually explain it better. Can we switch to the whiteboard? So as you're sending your signal, it's like up and down, up and down. And then you have that long gap. And then when you want to repeat a signal, instead of sending the whole signal again, you can just send a positive. And that just means repeat. So that's just send this again. So if a protocol requires you sending a signal twice, send the signal once, and then you just repeat. And repeat just means staying high. And what's interesting about that, if you've ever kind of messed around with a TV remote, if you're clicking the if you're clicking the volume up button like repeatedly, your volume will climb slowly. But if you hold the volume up button, the volume will crank up really fast. The reason for that, if you click the button, you have to send the whole signal with the repeat, the address, the header, all of it. If you hold the button, you can do the header, the address, all that once, and then the remote just stays high. It just stays on. That light just stays turned on, and the TV detects, oh, I need to repeat that command, repeat that command, repeat that command. So it's just a shorter portion of the signal. It's more efficient that way. Let me know if there are questions, because I imagine this is where it's going to get confusing. Yeah.
What?
That depends on the protocol. So he asked why there's an inverse. Certain protocols require the address and then the inverse, and then the command, and then the inverse. Some protocols require just the address, the command, and then the repeat. And like I said, the repeat, you can just stay high. Some protocols require the signal being sent 3 times. I think Samsung's protocol requires, maybe it's Sony, one or the other. But you have to send a signal 3 times for it to actually happen. If you only send the signal once and then a single repeat command, the TV just ignores it. It's just the rules of the language. We can go past it. So how the signal is read. I meant to mention this earlier. IR communication is kind of like playing Morse code with a flashlight. When you're blinking an LED, that's just creating a Morse code for the receiver to pick up. So we all know like ... dash is SOS. Data communication kind of works the same way, where it's not whether the signal is high or low that determines what you're actually sending, it's the length of time. A dot is a short press on Morse code, a dash is a long press. You can see in the signal, as it's going up and down, there's different gaps on how long it's staying at zero. The signal being high and low, it's staying low for different amounts of time. That amount of time is what determines what you're trying to tell the receiver. If it's a short span, 1.25 milliseconds on the picture, that's a 0. If it's a 2.25 millisecond pulse, that's a 1. It's the length of time. Zeros are a short press, 1 is a long. Does that make sense? So again, this is kind of the same thing, kind of drilling it in. So you have bit 1, bit 2, bit 3. As you're building up your data stream, your bit.
Yeah, I can hear.
Okay, well, I was trying to find out what the question was.
Kyle asked a question. Which question?
There was a question.
Yeah, what was the question that you were answering?
I think I asked if it made sense.
Oh.
I basically asked 4 questions.
If there was no question, then I don't know. It's hard to hear anybody in the chat.
If there was a question, just ask again. So as we're looking at this signal, bit 1 will be a 1, bit 2 will be a 1. So if we were to build this signal, it would be 1, 0, 0, 0, 1, 0, 1. So this signal is what's actually being sent. That's what you're telling the receiver. But the way it's done is based off the gaps of how long these pulses occur. This is probably not very visible, but this image is really good. So again, talking about that length of the pulse, there's multiple different ways you can do it. This one, the pulse distance coding, you're talking about start of pulse and next start of pulse. Pulse length coding, you're talking about how long the pulse was. So it's basically talking about, are you focusing on how long you were at 0 or how long you were high? It's just the different portion of the signal you're measuring the time of. Probably a good way to explain it.
What?
Yeah, we're not going to talk about. And then the other part of signal sending is you have to modulate this. I actually want to kind of go over what we've talked about already. So you have the head of your signal, then there's this gap, which is space, and then you're sending zeros and ones. On the bottom, we just kind of have a standard signal, which you would expect to see. But it doesn't really work out very well if you do it that way. So IR signals are actually modular. And what that means, if we switch to the whiteboard, instead of just sending a flat signal like this, we're actually going to send a signal like this. And just the time, it's basically the LED blinking on and off. And while you're blinking on and off, that's considered a 1, opposed to just going from off to on, staying on, going back to 0. You're at 0, and then you blink on and off, and then you go back to 0. And that amount of time that you are blinking, that's considered a 1. Yes, the toggling is considered. There's a few reasons for that, and I have some slides on it. So this is what modulation looks like in an actual signal. This is, again, what I picked up with my own oscilloscope. So these blocks are, if you zoomed out, they would just look like a solid block because it's blinking so fast, but it's going up and down between 0 and 1 very, very rapidly is what's actually happening. Go to the next slide. And the reason we want to do this, I pulled this off of the. It's very hard to create a sharp square signal. So even with this modulation, the signal isn't staying as a nice rectangle. You kind of have spikes and weird behavior at points. That's the ringing. That's the signal just not being perfect, whether it's the voltage being weird, the current being weird. It could be, there's tons of variables. Remember, these whole signals are sent in a couple milliseconds. So we have really tight margins to work with. And instead of depending on a perfectly square signal happening, we use this blinking to kind of eliminate the need for that perfectly square signal. Kind of makes it easier on all the components and the program. Just makes it more reliable. You also have to consider, if you want a perfectly square signal, it's kind of physically impossible to go from 0 to 1 instantaneously. There's kind of like a ramp up time, and then there's the ringing, and then it kind of levels out and stays at 1. And then at the end, when you want to go back to 0, it takes a split second to go down to 0, and then it rings, and then it stays at 0. You just don't get a good waveform that way. And by blinking, it kind of builds in a little margin, a little room to work with. So putting it all together, again, we have a signal head, we have a gap, we have our length of time, whether it's time staying at 0, length of time staying at 1. We're using those time lengths to create a signal of 0s and 1s, and we're modulating our signal. This demodulated IR signal, I mentioned before that the IR receiver, the 3-pin version, is able to receive an actual signal and demodulate it. This modulation occurs at different frequencies. A really common one is 38 kilohertz. It depends on your protocol. Sometimes it's 22 kilohertz. Sometimes it's 38. Sometimes it's other weird numbers. That frequency, the bouncing, occurs at a certain frequency. And our 3-pin modulators are able to pick up and remove that modulation at certain frequencies. So if you have a 38 kilohertz signal, if you have a 38 kilohertz receiver, it automatically takes that out and gives you that nice clean signal that you want. Something else to say. It's going to bother me. I lost my train of thought. There was something I really want. So another reason that we want modulation, these receivers just pick up IR light, which we talked about. Candles emit IR light. The sun emits IR light. We want to ignore that. By adding in this modulation, the receiver is looking for a signal bouncing at whatever frequency, whether it's 38 kilohertz, it's looking for a signal, a light signal it wants a signal that's changing at that frequency. So just a straight light coming from a candle, it's going to ignore that. Thank you. No one wants to hear gross throat sounds.
That's why I want.
So again, this is a signal that I picked up using my own oscilloscope. This orange signal is the transmitter. And remember, it's solid looking because we zoomed out on that modulation. If I zoomed in, it would be bouncing really quickly. But I zoomed out enough that it just looks like a solid block of. And this red signal is what the receivers. You'll notice they aren't solid blocks of color because it pulled out that modulation automatically. It turned that modulated signal, that bouncing signal, into a nice clean waveform that we can interpret into ones and zeros very easily. Also notice, kind of interesting, the receiver starts high and gets pulled low, whereas the transmitter starts low and goes high. So on this orange signal, when it's low, that's when the light is off, the transmitter is off. When it's high, the light is on. Whereas with the receiver, this red line, it's normally high and it goes low when the light is on. I don't know why that's a standard, but I've always seen it done that way. All receivers are normally high. I don't know the exact reason. So the entire process, if we want to look at from beginning to end, we have an encoder, just a chip that wants to send a signal. This is your remote. The remote gets a button press and it says, I want to send a signal. Creates a modulated signal. This IR LED at the end of your remote sends a modulated IR signal. It blinks. That's what sending a signal is. It just blinks. The receiving IR diode, that would be just the IR detector in your TV, picks up that signal. It demodulates it into a binary signal. And then I'm talking about TVs, so the microcontroller would actually just be a TV. Then gets that signal, recognizes that as a command, and then performs the command. That is the kind of entire process from beginning to end, how a signal is created to receive. The end of part 1. Well, part 2 isn't.
2 is.
That'll cost you extra.
5 now. So is that it for you?
If there's any questions.
Question?
I have a question. I'm not sure if you can hear me. I'll type.
Don't be shy, guys.
I'm hearing none, so I'm going to pose my own question. Was this interesting?
My opinion. Really?
The uses.
It's a great way to.
I mean, yeah, it's fun to see like the practical use, why it matters, what you're doing with it.
Kyle, question. That is definitely. So,
Thank
good
you.
mark. I think he did because technically.
Oh, yeah, what was that again? Yeah, you're not looking at the amplitude, the value of high or low. You're looking at the length that you're staying high or low.
like a frequency as a maybe more wave.
Wavelength would probably be a better way to think of it. Yeah, so like if you think about Morse code, you're only sending a signal when you're pushing the button. You're not, like if you think of pushing the button as a 1 and not pushing the button as a 0, you're only looking at ones to pick up the signal, and it's the length of time that you're staying on the button at 1. That's what turns into your dots and dashes.
I wanted to know, but pair octocouplers. I know that it's certain circuit question is going to be more robust power output, but I don't really see why IR communication receivers can't be used for optical isolation, assuming the components are able to handle the stresses. It's better if
Yeah, I'm trying to read over your shoulder.
it's okay. I tried to do the best Kyle voice I could. It was the best one I had at the moment.
I'm gonna be honest, I don't know what an octocouple.
We have a okay, Kyle, can you describe what an octocoupler is?
I probably can't answer the question because I don't even.
Yeah, flexing on this 8 couples. Couples all working together. They're really small, Ant-Man sized couple.
Well, you said opto with a P.
Opto? Oh, I thought it said oct or IR and a detector. Oh, yeah. Sorry, I messed that up. Okay. That might be more on like the electric scale. You can answer that.
I don't really feel comfortable answering because I don't know.
Okay, that's understandable. They may be very similar. Like I want to say, throwing out a possibility that regards, I don't think that the most
From an electrical perspective,
yeah,
I imagine they just have a different, possibly even the same protocol.
might be.
No,
No.
the protocol is not built into the board. The controller doesn't, the controller is just telling the LED to turn on and off.
Oh,
The only thing that knows about the protocol is well, my use is different because I'm not sticking. So yes, the receiver and the transmitter would know the protocol. Whereas
probably.
yeah, if you're using like a Samsung remote, it can't pair with a different TV.
Yeah.
Because they use a different protocol. Yeah. Whereas when you're using like a universal remote, if you've ever seen one of those, like just a generic universal TV remote, you have to pair it with your TV. And what it's doing when it's pairing is actually just determining what protocol it needs and what frequency it needs. It's not like creating a Bluetooth connection or anything. It's just figuring out what's my blinking pattern. What are the rules that this TV is expecting?
Kyle said it sounds like a second schematic. One is analog and that's different. Okay.
Yeah, it looks like it's just transmitting a signal. Anode and cathode is just sending out light to my understanding. I don't know what the drain.
That's how it works.
Well, cathode is ground. Well, it's analog. That's interesting. So it can send a wave instead of like a square structure.
Dragging.
Like a power station?
Talking about drain. Opto. Are you talking about opto coupler or are you talking about the drain? Opto coupler. Okay.
Oh, like okay, so like how they work in combination, I imagine it'd be pretty simple because it's just sending a signal and receiving that signal.
I may have to poke my remote. What? Okay. I think that's the end of the lecture.
Well, one thing I do want to mention before we sign off, we're kind of planning a part 2, and well, next week we have the election.
Election.
Potentially. But kind of a preview towards that, and the reason this whole IR discussion came up. I'm currently interning at the Rock and Roll Hall of Fame, and I'm developing a universal communication device. Yeah. What do I need?
Well, actually, that way, show.
So I'm working on this prototype. We have an ESP32 microcontroller, which is kind of the brains of the operation. My device is able to receive an IR signal and retransmit IR signal. It stores an incoming signal, can store multiple save them for later, and then retransmit them when desired. My device is a little fancier than kind of what we were talking about because I had to code my own IR class. We want this to be universal. And we kind of wanted to get around the whole protocol thing. When you use an IR class that you find online, they're just looking at those gaps of time that I was talking about, where it's the length of time that you stay high or low, that's your ones and your zeros. Classes that you find online, they just look at that. I built a class that picks up an entire signal, high and low, the entire modulation. It does not demodulate. It picks up the entire signal and then is able to retransmit an entire signal. And since it's ignoring modulation, it can take any protocol from any remote, and it can take that in, store it, retransmit it, and it will function properly. And that's just the IR portion of this device. There's other aspects to it where if a device doesn't use IR to communicate with it, it's able to compensate for that too. This is meant to communicate with any device. Be careful. The rock hole.
They're trying to track you. The government's on.
It's still just a prototype. I'm actually, within the next week or two, going to be putting it on a proto board with soldering. And then eventually, once it's all the software is written, there will be, like, we'll be printing our own circuit boards and then creating like a 3D printed case for it.
So that sense, that also that your device could also touch by burning bowl, as you said, correct?
That's an interesting question. Just to repeat for the recording, he was asking, since it's meant to be universal and can pick up any signal, could it pick up a signal from a candle since that also emits IR light? Man, that's interesting. I imagine it could pick up a signal from a candle, just the same way that a Wii remote can pick up a signal. There's no reason that this couldn't, because it's just looking for any signal.
As long as none of the generators go out at the rock hole, they're with that.
Well, it also has a JSON file where it, like, if you reboot it, turn it off and turn it back on, it goes back into the state that it was in. So, like, if you have signals stored into it, when you turn it back on, it'll still have those stored. Yeah.
IR out of
Would it, like, accidentally overwrite something? Yeah, we'll talk about it more at the next lecture, but do we have a data cable? I meant to grab one before I left, just like last time, but I forgot again.
It's okay. We can always.
Yeah, I definitely want to do a demonstration next time. I need to remember that. But it doesn't just always pick up a signal. You have to tell it, hey, I'm about to send you a signal. It gives you LED confirmation, hey, I'm about to pick up a signal. You give it a signal, it stops receiving stores.
So I'm going.
Yeah, the header.
So it has some.
It's not looking for a header at all. It does not, my class does not require any protocol. Any signal, it will pick it up.
So go. Not a say that one like power.
What if a terrorist flashlight is just somehow IR flashlight?
It would ignore it unless it's in a receiving state. You have to tell it to receive it.
I think you talked about it. Active tells it. Said that
Well,
only.
There's buttons right here. When you push a button, I don't remember if it's this one, but you push the button, one of these LEDs will start blinking. That means it's ready to pick up a signal. You push a button on your remote, it'll stop blinking, saying that it picked up the. But until you push that button, it's just going to ignore everything. You have to put it into that receiving. And then the receiver will pick up any, whether it's a candle or what, it's just going to pick it up.
Flash Ohio said, gotta go, guys. Talk, Brian. With us. Fantastic. Esteban's typing something. Shut it off. You all set? Much?
And again, we'll talk more about my prototype next time.
Did everyone enjoy the lecture?
Thank
Sam,
you.
did you enjoy the lecture? Pay attention. Okay. Yeah, quiz on Tuesday. We're ready mid.
This will count towards your finals of your classes.
About 90% of what you had and now. So
Dr. Thomas is writing the exam.
Dr. Thomas is writing the exam. Oh my God, you're straight here into the heart. Fuck.
I did not build it.
So you just threw this.
It's progressed over time because I started with just pairing these devices, which is a built-in feature. There's no other circuitry required. And then over time, I was like, oh, I need an LED. And then over time, I was like, oh, I should add some buttons because that'll help me out with the debugging. And then eventually I needed IR parts, so I added that in. It's just kind of like built on its own. So yeah, there's not really a set schematic file that I have yet, but when we do make a printed circuit board for it, we will need a definitive final schematic eventually. I have used flowcharts though. So there's kind of, I don't want to say protocol.
This is called chaotic.
It is a little chaotic.
I'm gonna throw it together, and if things get in my way of doing that, then you know what? I'll just okay. I need that.
Well, kind of on that point, when I got the job, my boss did not have any specifications made for me. He was just like, this is what I want, start working on it. And I've kind of had to make it up as I go. And I mean, he's guided me, added like ideas, like I want you to do this or more like this, change this, whatever. But I've also added in more ideas as I've gone along, like, hey, it'd be cool if we had this feature, let's add that in. And then you have to make changes. There's nothing really set in stone from the beginning. It's very much a work in progress. Yes, I'm the only person working on this project. My boss is overseeing, but this is entirely my own.
Bring this in for design project.
If I didn't tell Adrian, I might be able to get away with that.
Just make now that I said it on here, you won't be able to get away with it. So I kind of shot off your foot, but 10. Oh yeah. Doesn't use schematics. I've never even heard of her.
Well, you probably.
What is that? Some kind of Italian dish? I've never been to that country. As enough we were. My mic.
Yeah.
All right. I just want to say thank you to everyone who decided for this wonderful little lecture. Bede, you did a fantastic job for your first lecture. This was awesome. I think this is a very interesting topic, and we'll definitely be having you back real soon. I hope you get that prototype up and running so we can, see it in action. I think that'll be really cool. Yep. So in the meantime, in talking about updated things, this coming the 10th of Monday, the candidacy form for the elections is closing, and then we will begin that Friday at the end of the fall break week, quote unquote. We will be doing what am I thinking of? The little debates, quote unquote, for the ACM candidates. I have not candidate sheet, so I'm going to take a look at it over this weekend and go ahead and figure out the candidates. So while you have a chance, if you'd like to be a part of the ACM, please do sign up for that candidacy sheet. It is pinned on the announcements, Discord. And other than that, thank you all for coming. And this lecture will be uploaded to the ACM YouTube if you'd like to watch it again. And thank you everyone for coming out here. Afro President. My